We're going to take a look at the check and reflect questions that we had on page 613. We had questions 1, 2, and 3, and then 8, 9, 10, and 11. Any issues with those 7 questions, please? Jill? Yep. Any others besides number 10? 9? Shelby? Okay. 1, 2, 9, 10? 8. 1, 2, 8, 9, 10. Any others? Okay. Listen, number 1, if you've got the right strategy, number 1's an easy question. If you don't have the right strategy, not an easy question. Okay, so what I want to point out here is not so much the answer to the question, but rather the strategy that we follow when we see a question like this. If you want to know what factors, bless you, if you want to know what factors influence something else, then what we want to do is get an equation. Find an equation that describes that. What are the factors that affect the magnetic force on a moving charge through an external magnetic field? What's the equation that describes that? Yep. Right. F is equal to QVB. So I wrote down that simple equation. We all know that, right? We all know that that's the equation that describes this. If we had a question involving math, that's the equation we'd use, and every single one of us would get it right. So we write down that equation. Now I want you to look at that question again and answer it for me. What factors affect the magnetic force on a moving charge? Let's say 3 of them. What's one of them? The charge. What's another one? Yep. The speed of the particle, the speed of the charge. What's the third one? The magnetic field strength, right? Now there is a 4th one actually here, and that is the direction. Because if the magnetic field and the particle aren't perpendicular to each other, then the force changes, right? So the angle actually matters as well. So we have to go in this case to these 3 variables in the equation, and then that 4th one, the angle. But that's rare that you're not going to get your entire answer just from the equation, okay? Because almost always when we have an equation, it's valid all the time, not just when they're perpendicular, okay? So it would be Q, it'd be V, it would be B, and then it would be the angle. Now question number 2 sounds real similar. It says, what are the factors that affect the magnetic force on a charge moving through a conductor in an external magnetic field? I'm not sure exactly what they want to ask me here. Okay, I know what they are asking. I'm not sure what they want to ask. Okay, if we go with what they're actually asking, then the answer would be exactly the same thing as it was for question number 1. Because notice they're asking us for the factors that affect the magnetic force on the charge. They're not asking for the factors that affect the magnetic force on the wire or the conductor. They're asking for the factors that affect the force on the charge. That's going to be Q, that's going to be V, that's going to be B, and then that's going to be the direction again. Now, I think what they want to ask here, not what they actually are asking for, but I think what they want to ask here is, what are the factors that affect the force on the wire, okay, the force on the conductor? Well, the equation that describes that would be F is equal to I times L times B. What factors affect the force on the conductor? The current, the length of the wire, and the magnetic field. And, of course, we know the angle matters as well, right? The direction matters as well. So if the wire is perpendicular to the field, this equation applies, it's all good. If it's parallel, the force is 0. So obviously, the direction of the orientation of the wire relative to the magnetic field makes a difference as well. So first one, it's QVB and theta. Second one, it's ILB and theta. Next question, number 8, says a wire lying perpendicular to an external magnetic field carries a current in the direction shown on the diagram below. In what direction will the wire move due to the resulting magnetic force? Doesn't matter whether we're dealing with a charged particle moving through a wire here or a charged particle moving through the air. In the end, this charged particle experiences a force due to the external magnetic field. We're going to use the hand rule for deflection here. Say thumb in the direction of the particle, which in this case is into the page. So thumb into the page. Fingers in the direction of the field, which is from north to south. Okay, it's to the right. Palm points upwards here. So the magnetic force in this case would be toward the top of the page. Okay? Right, thumb, fingers, palm points towards the top of the page. Number 9 says the battery supplies a current of 5.2 milliamps. We're going to want to Circle that right away because that's a non-standard unit, right? Milliamps. We haven't seen that a whole lot lately because we've been using a lot of hand rules and stuff, and we haven't had to worry so much about things like milliamps and stuff like that. But whenever you see non-standard, remember to circle it. Okay? We're going to determine the quantity of charge that goes through in 2 seconds. This is our time. This is our current. We want to find the charge. So we're simply going to say I is equal to Q over T. And remember we did that one day. That's the equation that describes the electric current that's going through a wire. Rearrange that to solve for Q. We get I times T. It's 5.2 times 10 to the minus 3 amps. We multiply that by 2 seconds. We get 10.4 or 1.04 times 10 to the negative 2 coulombs. And finally, question number 10 says 2 conducting wires parallel to each other carry currents in opposite directions. Using the appropriate hand rule, determine whether the wires will attract or repel each other. This is a hard question. Although we did do something like this when we introduced the idea of magnetic fields. I'm not sure if it was this exact question or not, but it was something similar to this, at least in terms of strategy. We have the electric current going in opposite directions. Let's say one's going into the page, one's coming out of the page. There's a circular magnetic field that surrounds both of them. The magnetic field surrounding the one that's going into the page is going to be, by the wire grasp rule, it's going to be counterclockwise. The one that's going into the page is going to be, out of the page is going to be clockwise. Right now, we want to find out whether these attract or repel each other. What I like to do is pretend we've got a couple little magnets. Okay, pretend this magnetic field is not caused by a moving charge, but rather it's caused by a little magnet. So let's pretend we've got a magnet up here. Let's pretend we have a magnet up here. What would be the polarity of each of those magnets if those were real magnets? They're not. They're pretend. They're imaginary. But if they were real, what would be the polarity? What would this end be, a north or a south? Be a north, because the magnetic field goes from north to south outside of the magnet, and it goes from south to north inside of the magnet. That's going to be north, that's going to be south. What about this one? That's going to be a south, and that's going to be a north. Again, the magnetic field goes from north to south outside of the magnet, and it goes from south to north inside. Are they going to attract or repel each other? They repel because south against south. Now, some of you are out there thinking, well, how did he know to draw these little pretend magnets that he invented above the magnets or above the wires? Why didn't he draw them below the wires, or why didn't he draw them somewhere else? It doesn't matter. Let's draw them right here. What's the polarity of these ones if we pretend there's 2 little bar magnets there? This is going to be south, this is going to be north, this is going to be north, because the magnetic field goes from north to south on the outside. That's going to be south. Are those going to attract or repel? They repel each other again. Well, what if I had to draw them right here? That's going to be north, that's going to be south, that's going to be north, what's going to be south. What are these guys going to do? Attract or repel? They're going to repel each other as well because it's north against north and south against south. So any way you look at it, it doesn't matter where you pretend these little bar magnets are, any way you look at it, it's going to be a repulsive force. If the current goes in the same direction, it's going to be an attractive force. If they go in opposite directions, it's going to be repulsive. There's only 2 possibilities here. Now you can remember those 2 possibilities. I wouldn't recommend it though. If you're anything like me, okay, you will forget. Okay, this is my, I don't know what it is, 60th time Physics 30? I don't know, something. I lost track after about 10. How many times I've taught Physics 30? Still, to this day, if you ask me right now, okay, whether 2 wires that carry current in the same direction attract or repel, I'll tell you the answer like that. Ask me tomorrow and don't give me a chance to draw it out, I won't be able to tell you. Okay, I don't remember that. Okay, every time I see a question like this, unless I've just done it like I just have, I'm not going to remember the answer to it. Even after 50 or 60 times through Physics 30. Okay, every single time I've got to figure it out. But here's the thing. I don't need to worry about that. Okay, if I ever get tested on that, I'm going to be able to do it. I never have to worry that I'm going to forget because I'm going to be able to figure it out every single time. Okay, that's what I would suggest to you as well. Be able to figure something like that out. Don't remember that when they're going in the same direction, they attract, opposite directions, they repel. Okay, we got enough to remember. Okay, you got lots to remember in social studies class and in biology class. Okay, you don't need to clutter up your mind with things like this to remember in physics class. Figure it out. Okay. Was that the last one that we had to do? It was, I think, yeah. Are we okay with that, by the way, guys? Did people understand what I just did there? I tell you, like you want to figure it out as opposed to remember it, but you got to understand how to figure it out. Otherwise, that's not much of a help. Okay, we have a test on Monday. I thought what I'd do right now is just take a quick, we can't review the entire unit. There's no way we can do that. But what we can do is real quickly go through a summary of the 3 hand rules that we've learned. Clearly, that's going to be a fairly big part of this test, right, the hand rules. Okay, there are other things on the test. Don't think that if you know these 3 hand rules, you're going to ace this test. Okay, if you know these 3 hand rules, you got a good start, a really good start. I would say that they're probably about as important as anything else, probably more important than most things that we do. But other stuff is on there as well. Okay? That's the thing, however, that tends to give people trouble. Not so much that hand rule number 1 is hard, or number 2 is hard, or number 3 is hard, but when we start mixing them, after we've done all 3 of them, then we start mixing them up. We start confusing them a little bit. So let's take a few minutes and work on those 3 hand rules. The first rule that we learned way back when in this unit was the wire grasp rule. Sometimes we just call that rule number 1. I was helping my nephew out on Saturday with his Physics 30. He had a test on Tuesday, and we were going over the hand rules, and I said, well, what do you guys call these anyways? They're the same hand rules, right? They do exactly the same hand rules as we do. I said, what do you guys call them? They call them rule number 1, rule number 2, rule number 3. Okay? We try to align ourselves with the textbook a little bit just so we can be consistent there. The wire grasp rule, and then the second rule we call the coil rule, although that's not what your textbook calls it, but that's what we call it. And then we have the hand rule for deflection. If you take a physics course in university, you may see them called the exact same thing. If you take a physics course in university, you may see them called rule number 1, rule number 2, and rule number 3, just like my nephew's teacher calls them. Okay, you may see them called something completely different. It doesn't matter. You may even see slightly different versions of these rules. That's fine. Okay, there's lots of different names for them. There's lots of different versions for them. Okay, don't worry about that. Okay, let's focus on when these rules are used and how we're going to use them. First of all, before we actually talk about when each of these are used, let's just simply distinguish between left and right hand rules, first of all. The left hand rule, number 1 or number 2 or number 3, or the right hand wire grasp rule, the right hand coil rule, the right hand deflection rule. What's the difference between the left and the right hander? Yeah. Good. The right is for positive particles. Now, when you see a question and you know it's going to be a hand rule question, okay, make sure you write down LH or RH. LH meaning left hand or RH meaning right hand. As soon as you see what kind of particle it is, negative or positive, write that down. Okay, because I'm telling you, I don't know how many times I've seen over the years. It would be literally probably thousands of times over the years that I've seen people get a question wrong, not because they didn't know what they were doing, but simply because they used their left hand when it was an alpha particle, or they used their right hand when it was an electron. Okay? Okay, identify that. Make sure that you don't, if you're going to mess up on this, don't mess up because of something silly like that. Okay, know whether to use the left hand or the right hand. Now, the wire grasp rule. What's the situation where we use the wire grasp rule? Now, as confused as we get sometimes, it's actually quite simple. We have a charge moving. Now, that charge may be moving through a wire. It may not be. Okay, we may have an electric current. Okay, I is electric current, right? We may have an electric current, which is a charge moving through a wire, or we may just have an alpha particle moving through the air, or a sodium ion moving through the air, or whatever moving through the air. We've got a moving charge. It will generate its own magnetic field. We want to find the magnetic field that's caused by the moving charge. That's it. There's no external magnetic field. There's no magnets here. Okay, there's no crazy apparatus here. It is simply a charge moving with a magnetic field that's caused by that charge, or a charge moving through a wire with a magnetic field that's caused by that current in the wire. That's all you got. All you're going to see is a charge moving or a wire, and it makes its own magnetic field. Use hand rule number 1 or the wire grasp rule to figure out what that magnetic field is. Rule number 2, the one that we call the coil rule, the one that your textbook also calls the wire grasp rule. I don't like that rule, that name for it, because it's essentially opposite to the wire grasp rule. So I don't want to call it the same thing when it's performed opposite to the other one. The coil rule involves a coil. What's another word for coil of wire, by the way? Starts with an S. Somebody said it? A solenoid. The good news is, if you forget that word and you're given that word on a test, well, there's probably going to be a picture as well. So if you forget what that word means, you're probably going to be reminded by the picture that shows a coil of wire. You get a coil of wire with an electric current in it. What we want to do is find the polarity of the coil. Right? The coil becomes an electromagnet. As there's an electric current going through it, it generates a magnetic field. We want to find the polarity of that electromagnet that's just been formed. Now, that's pretty similar to the wire grasp rule. Not necessarily in how we do it, but in where we use it. The wire grasp rule says, look, we get an electric current. We want to find the magnetic field. Coil rule says, look, we get an electric current. We want to find the magnetic field. Except in rule number 2, it's specific to a coil. It's not just any time you have a current. It's when you have a current going through a coil of wire or going through a solenoid. The third rule, which is the deflection rule, this is the one that's quite a bit different than the other two. This is where we have a moving charge, just like we did in rule number 1, a moving charge or an electric current, and magnets. We'll call that an external magnetic field. Maybe you've got magnets, maybe you've got the Earth's magnetic field, whatever. You've got some kind of magnetic field that's not caused by the moving charge. Something that was already there, an external magnetic field. We want to find, in this case, not the direction of the field. We want to find the direction of the magnetic force. So what's the difference between these 3 rules? Well, rule number 1 and rule number 2 are really, really similar. You got charges moving, you got a magnetic field that's caused by those moving charges. The thing that differentiates the two, well, rule number 2 uses a coil, rule number 1 doesn't. That's it. That's the only difference between when we use those rules. What separates rule number 3 or the deflection rule from the other two? Well, in rule number 3 or the deflection rule, we've also got an external magnetic field. If you see magnets, then you're going to use rule number 3. Okay, if you don't see an external magnetic field, then you're not going to use the deflection rule. You're going to use one of the other 2 rules. Now, how do we do them? It's great to know when to use them. And that's more important than anything else, knowing when to use them. But once we know when to use them, we also have to know how to use them. Okay, rule number 1, or the wire grasp rule, says, take your thumb and point your thumb in the direction of the moving charge, or the direction of the electric current. Take your fingers, bend them, and you want to point those fingers in the direction of the magnetic field. Not just any magnetic field, though. Remember, there's no external magnetic field here, so don't point them in the direction of any kind of magnets. You want to point them in the direction of the magnetic field that's caused by the moving charge. Right? It's thumb, clench your fist, fingers are going to point in the direction of the magnetic field that's caused by that moving charge or caused by that electric current. Rule number 2, well, we also have our thumb and fingers. And our fingers in this case are also bent, right, like this. But this time our thumb points in the direction of the magnetic field caused by the electric current. Remember, we're always dealing with a wire here in the coil rule, so we're not going to say moving charge, we're just going to say the direction of the electric current. And our bent fingers, sorry, that's wrong, that's backwards. Our thumb is going to point in the direction of the magnetic field caused by the moving charge, or the magnetic field caused by the current. And our bent fingers are going to point in the direction of the moving charges, or point in the direction of the current. So it's exactly opposite to the wire grasp rule. I was joking with the last class. Maybe we shouldn't call it the coil rule. Maybe we should call it the rule grasp wire. Instead of the wire grasp rule, the rule grasp wire. Because it's exactly backwards from the wire grasp rule. If we stick our thumb one way and our fingers the other way in the wire grasp rule, then in the second rule, the coil rule, we're going to stick our fingers the first way and our thumb the second one. Exactly opposite here. The third rule, called the deflection rule, or at least what we call the deflection rule, once again, we've got our thumb and our fingers. This time, though, our fingers aren't bent. Our fingers are straight. And we've also got a third variable, which is the palm of our hand. Make sure that when you're using this hand rule for deflection, thumb, fingers, palm, make sure they're all 90 degrees to each other. Right now you can see my hand. Okay, my thumb points on the x-axis, my fingers are on the y-axis, my palm is on the z-axis, right? So we've got 3 axes there. We can't just go do something like this, okay, and kind of put our thumb in the direction of the fingers. We've got to make everything 90 degrees to each other. Otherwise, this rule doesn't work. My thumb will once again point in the direction of the moving charge, or whatever way the electric current is. My straight fingers will point in the direction of the external magnetic field. That's the magnetic field that was already there. And my palm will point automatically in the direction of the magnetic force. So the first rule, the wire grasp rule, it's thumb, fingers, that's the way the magnetic field points. In the second rule, the coil rule, it's fingers, thumb, that's the way the magnetic field points. In the third rule, it's different, because in the third rule, we've got magnets now. We've got an external magnetic field. And we want to find not the direction of the field caused by the moving particle, but rather the direction of the force that's acting on the particle. Okay. Thumb, fingers, palm points in the direction of that force. All right? I'm going to do one example of each, but I'm not going to necessarily do them in the order that they're listed here. Okay, I'm going to put up an example on the board, and I want you to tell me which rule I'm going to use, the wire grasp rule, the coil rule, or the hand rule for deflection, and then we want to do it. Here's the first one. There's an electric current going through this wire around a piece of steel. What rule are we going to use for that? The wire grasp rule, the coil rule, or the hand rule for deflection? This is the coil rule. Obviously, this is the coil rule. Now, don't get confused here, guys. If you get a question that already has a magnet with a north pole and a south pole, you've got a different problem altogether. Okay, when we use the coil rule, we're trying to find the field that's induced here, the magnetic field that's caused by the electric current. Okay, we're not trying to do something with a magnet that's already there. We're trying to do something with the magnet that we're causing by this current. All right, so the current's going to go from the negative end to the positive end. It's going to go up in the back, down in the front, and then it's going to go around this way. So it's going to go counterclockwise, essentially. Let's take a look up here and take a look at my hand. Okay. This copper pipe here represents the coil of wire. I want my fingers to point in the direction of the current here. Remember? Remember how the rule worked here? Okay, for the coil rule, my fingers are going to point in the direction of the moving charges. Fingers are going to point in the direction of the electric current. It's going to be down in the front. Okay, fingers down in the front. Which is my thumb point. Okay. Got a thumb is pointing towards the left, right? So that means the magnetic field inside this coil would go this way. Inside the coil, it goes this way. That means this end is what? North or south? That's north. This is south. The magnetic field points from north to south outside the magnet, but from south to north inside the magnet. So basically, in that rule, your fingers are going to point towards the north. Okay? Yeah. Okay, let's do another one. What's the direction of the magnetic force on this moving charge? Which hand rule is it? First of all, which hand is it? Left or right hand? Left hand because it's a negative particle. Is it the wire grasp rule? Is it the coil rule? Is it the hand rule for deflection? Deflection, how do you know that? Because what? Yeah, you've got magnets here. You've got an external magnetic field. So it's going to be the hand rule for deflection here, right? You're trying to find the force. You got an external magnetic field. It's going to be the hand rule for deflection. Remember how that one worked? It said thumb in the direction of the moving charge, fingers magnetic field, palm points in the direction of the force, thumb to the right, fingers down toward the bottom of the page, palm points out of the page. So the magnetic force in this case would be out of the page. And the third rule, the third problem, I should say, we've got an alpha particle, let's say, going into the page. What's the direction of the magnetic field that's caused by that alpha particle? It's going to be a right hand, and it's going to be the wire grasp rule, because it's just a particle that's moving, and we want to find its magnetic field. Thumb, fingers, it's going to go clockwise. Now, these are the questions you're going to get. These things may be buried in 3/4 of a page of information about some context that you've never heard of before. You may have to do the wire grasp rule in a completely new context than what we've done here. In fact, we've done it in no context here, right? It's just, here's the particle moving this way, what's the direction of the field? You may have to read through a bunch of stuff and strip it down to make it into one of these 3 questions. Okay, but they're all like this, if we can strip them down. Okay? If you get 3/4 of a page of information, then take away what's not important and make it into some little blurb like we've got drawn on the board right there, which makes it a fairly easy question. Okay, telling you right now, you will see this stuff on the test. I'm also telling you right now, okay, it may be as straightforward as we've just done. It may be buried, and you've got to find it. Okay, so find it. Dig it up and find it. All right? I want to take a look at 2 multiple choice questions here now. 2 multiple choice questions that would absolutely be fair game for Monday's test. Even though Monday's test is a magnetism test, okay, I think I told you yesterday that you can expect to see a little bit of electricity on it. No crazy electricity questions, certainly not the depth that we saw in our electricity test, but things like electric fields, just to see if you can distinguish between gravitational fields and electric fields. These are 2 great questions that illustrate not what you're going to see exactly on Monday's test, but the type of thing that you could see. The level of unit 1, the level of our last unit that you could expect to see on Monday's test. This says diagrams 1 and 2 below each show an electron as it enters a field. The fields are different, but the electrons enter them with the same instantaneous velocity. Before we read anything else, we can identify that this would be an electric field and that this would be a magnetic field. So if we've spotted that, then we should write that down. Okay, we know we're dealing with 2 different fields. They tell us that, and we know that if we look at it closely, we're dealing with an electric and a magnetic field. Now, We've got 4 observations here, 4 statements about the motion of the charged particles as they travel through the fields. 4 statements, 1, 2, 3, and 4. Number 1, the speed of the particle remains constant. Let's take a look at both of these things here. Before we even read question number 88 and 89, let's take a look at both of these diagrams, and let's identify whether each of these statements is correct or not for each of these diagrams. Statement number 1. Does the speed of the particle remain constant in diagram number 1? Christina, what happens to it? Good, it speeds up, it accelerates, perfect. It's like a car going down the hill, right? This is an electric field. Charged particles accelerate in an electric field, so the speed of the particle does not remain constant in diagram number 1. Does it remain constant in diagram number 2? That's a magnetic field. There's an electric force on the charged particle right here in diagram 1 that causes it to speed up. There's a magnetic force in diagram number 2 that causes it not to speed up, but rather change direction. We would say thumb in the direction of the particle, fingers feel, palm points out of the page. There would be a force acting on this particle out of the page. It would start going in a circle like this out of the page. But does its speed change? No. Forces will either change speed or change direction or change both. And the first one here changes speed, and the second one it changes direction. So observation number 1, does the speed of the particle remain constant? Yes. Its velocity doesn't because it changes direction, but its speed does. Okay, let's look at observation number 2. The speed increases. Well, if the speed doesn't remain the same, then yeah, it's going to increase. It's like that car going down the hill. And in diagram number 2 here, if the speed remains constant, then it's not increasing, so that doesn't work for us. Observation number 3. The direction of the particle remains constant. When this particle goes from the negative to the positive plate, does it change direction as it speeds up? No. Okay, so we're going to put an X by this one. Sorry, we're going to put a check mark by that one. The direction remains constant. Observation number 3 for the second diagram. What's the shape of the path of a particle in a magnetic field? Circle, right? So this is going to be an X. Observation number 4. Does the direction of the particle's motion change? Oh, if the direction remains constant, then it's not going to change. If the direction doesn't remain constant, then it is going to change. So let's look at our questions now. What are we actually asked for in these 2 questions? The statements that describe the motion of the charged particle in diagram 1 are, it would be 2 and 3, C. The statements that describe the motion of the charged particle in diagram 2 would be 1 and 4, so it would be B. You guys comfortable with that? Now I'm curious, we didn't do this, didn't have you sit and do this just because of time issues. How many people would have got those 2 questions? First time through, okay? I think those are good questions, but I think they're a little bit more challenging than average. Okay, there's a little bit to them that we have to think about there. Okay, we've mentioned this before unit tests. Remember these questions. I'm not suggesting that you're going to see these questions on the test. You won't. But remember these questions. Okay, when you see your test and as you're preparing for your test on Monday, okay, think about some of the questions that had a little bit of a challenge to it. Okay, they're doable questions, but these are questions that had a challenge to them. The questions on your test will too. Okay, it's stuff that you know, but it's questions like this that just have a little bit of a twist to them. Sometimes, right? Sometimes have a little bit of a twist to them. So go through all of those multiple choice questions. We've done a lot of them already in class. Go through them again. Every single one of them. If you need a blank sheet of paper, or if you need a blank copy of all those, just go on the website and download another copy of them. So they're completely blank and there's no work on them. Do them all. Okay, practice that stuff. Okay, prepare yourself not only for the topics that we do, but also, little tricks, little intricacies of questions like this that we have to kind of think about a little bit. All right? You feel okay with that? Good.